In this lecture, we're going to continue the discussion of radiation from a moving point charge. Um, and so in the previous lecture, I made the statement that why don't we solve this where we define this velocity u as the speed of light times the propagation vector minus the speed of the moving charge. Let's try it where V was 0. Let's say it's initially at rest when it emits radiation. Okay. Um, Now, we could, instead of saying it's initially at rest, we could say it's non-relativistic. And so if it's non-relativistic, so basically the speed V is much, much less than the speed of light c, then we could make the approximation that u is approximately just the speed of light times the propagation vector. And then everything would be exactly the same. So I don't have to necessarily pick just that one very simple case of v is equal to 0. I could just say maybe it's moving really slowly. And if that's the case, then I should get a similar result. I should get the same result, really, by my approximation. Okay, now if I want to try and solve it for any value of v, from 0 all the way up to the speed of light, then that becomes a much trickier problem to solve mathematically. So instead of doing that, what I think I'd like to do is to follow the analogy that's set forth in the book, and that is to consider, let's say, that the power is the change in the energy with respect to time. And so this one, dW dt, is the energy per time, basically measured at r now. So it's measured at the time t right now. Now, the power that is emitted would be the energy at the time when it was emitted, tr. So I would call this energy per time leaving the source. Okay, now if I want to relate those two, what I would essentially do is say that the power that was emitted is equal to the power that is measured times this factor. Basically, I would just expand the partial derivatives. So I would look at how my time is changing with the other time. So dt, this right here, which I can't really say, essentially is the conversion factor between my frame of reference and the charge's frame of reference. Okay, so if I go back and look in the lectures from chapter 10, I can relate this distance r to c times the change in the time. And I could also now square it. So I would have r squared is equal to r dot r, which is the same thing as saying c squared times the change in the time squared. And now, if I take the derivative of this, so the derivative of with respect to time of r dot r is c squared, the derivative of this time difference squared. Okay, so let me see. So if I don't call this r squared, if I keep the dot product, I basically have to apply the derivative through the chain rule. So I would get the r dt dot r plus r dot dr dt, which is then equal to 2c squared t minus tr times this partial derivative, 1 minus dtr dt. Okay, so sorry, getting a little messy over here. Okay. So that means on the left-hand side, I have 2r dotted into the change in r with respect to time. And I would get, let's see, 2c r. So c times the change in time is just r, times 1 minus this partial derivative of times, like so. Now remember that r is the position from the measurement from the origin to my measuring position, that's r, minus the path, like so. So if I want to take the derivative of this, I have to say 0, my measurement point doesn't move, minus dw dtr dtr dt, which is essentially minus the velocity of the charge times this conversion factor right here. Okay, so now if I put that in to the previous equation, I get 2r dot v with a minus sign dtr dt, which is equal to cr minus cr dtr dt. And now I can combine terms, and I should get cr is equal to dtr dt, cr minus that, which if you remember before, that's just the dot product of r and u. So I can now rewrite this as cr like that. And that's the term that we're looking for in our equation for the electric field. So in the end, dtr dt is cr over r dot u, like so. Okay, so then if I go back and look at my powers, the power emitted is equal to r dot u over cr times the power measured. Okay, so what is this factor right here in front? Well, if I look at this, I have r dot u over rc is equal to cr minus r dot v over cr, which is 1 minus r dot v over cr, and that is essentially the Doppler effect. So it's the effect I see of a change in the wavelength or frequency of the radiation that is emitted to when it's actually measured. So if you think about it, I now have a moving source, the charge, and a stationary receiver. And so this factor in front of the powers is the Doppler effect. It's a change. Okay. So the next thing I can do is consider how much power I'm capturing over a solid angle. D omega. So d omega, so r squared d omega is r squared sine theta d theta d phi. So it's essentially, if I look at this solid angle here, like so, then this is r, this is d theta, and this is d phi. So the solid angle is just like the angular area. So it doesn't depend on the radius. It just depends on the angles. So the change in power with respect to the solid angle would be R dot U over RC times 1 over mu 0 C, the radiation from the field, times R squared. Okay, so now if I put in the equation for the electric field, then what I would get is R dot U over RC squared mu naught times R squared Q squared R squared over 16 pi squared epsilon naught squared times R crossed into U crossed into A squared over R dot U to the 6th power. Okay, so you can now start canceling a whole bunch of R squareds and things like that, and what you should end up with is Q squared R cubed over 16 pi epsilon naught R crossed U crossed A over R dot U to the 5th power, and then the numerator up there is squared. Okay, so now if you remember that R hat is really the vector R divided by the magnitude, that means R is equal to the magnitude times the unit vector, which means that this change in power over solid angle is Q squared R cubed over 16 pi squared epsilon naught R to the 5th R cross U cross A squared over R hat dot U to the 5th power. And then, let's see, how else can we clean this up? Okay, well, I can cancel this and make it a squared, and then I can take that squared and put it into the numerator, and so what I get is Q squared over 16 pi squared epsilon naught R hat times U crossed into A quantity squared over R hat dot U to the 5th power. Okay, so now everything is in terms of the unit vector R, and if you integrate that, so I now integrate over the solid angle, so I now take that integral over that, I get a power which is mu 0 Q squared gamma to the 6th, which I'll explain in a second, 6 pi speed of light, A squared minus V crossed A over the speed of light, that whole thing squared, where gamma is this factor of 1 over the square root 1 minus V squared over C squared, which should look familiar from general relativity. Anyway, so this is called Leonard's generalization. Okay, so I'm going to stop here, and then in the next video we'll go through and kind of talk about the consequence of this.